So the next topic is duality. It's a whole world. It's an absolutely beautiful subject. You can think of it many different ways. It's one way to think of it is it's a way to it's an organized way to form highly non-trivial bounds on optimization problems, and we'll see that that's one of its beauties, even for hard problems, not necessarily convex. We'll also see that it's for convex optimization problems. There's a beautiful theory. It will lead to things like optimality conditions that give you that in a few handful of cases you can solve, but always would give you insight into how a convex optimization problem works or what the solution is going to look like. And finally, we'll see that you can interpret some results from duality as giving you a sensitivity of the optimization problem to perturbation and sensitivity analysis of various things. We'll look at a bunch of examples, and we'll extend this to generalized inequalities. That'll be the last thing that we'll do in this section. I should say something else about it. I mean, of course, a lot of it is just theory, and it's absolutely beautiful. And a lot of the theory works even when the problems involved are not convex. The difference is when they're not convex, you can't actually do it in a sense, because you're actually asked to minimize various things. And roughly speaking, you can't do that unless the functions involved are convex. So what's very interesting about duality is that it becomes, although it's interesting theoretically, always, it actually becomes actionable in the case of convex optimization. So it's actually, you can do it, you get numbers, and they have beautiful interpretations and so on. So that's the idea. Beautiful subject. All right, so we'll start. And for a while, I should say, we're just going to be defining various things and going very slowly, but you'll see actually even after just a few pages, we're going to end up with something that's actually highly non-trivial and interesting. So let's start. So I want to start with a standard form problem, and I'm going to not assume it's convex now. So I minimize an objective subject to inequality constraints and equality constraints. And I'm going to form a Lagrangian. And a Lagrangian is this. I'm going to add to the objective a sum of the lambda i's are going to be non-negative numbers here. I'll get to that in a minute. Multiples of the of the constraint functions here, and I'm going to add some other numbers. These are going to be unconstrained, the new i's. That's going to multiply hi of x. You should think as a residual. It's the amount. If it's 0, that's perfect. That means you satisfy that constraint. Otherwise, it's a residual. So that's the idea. That's the Lagrangian, and it's a function of both x and these things. And one nice way to interpret the lambda and nu vectors is, if you like, you could think of them as prices, right? So for example, f0 of x, let's assume that's in dollars. f1 of x, well, I don't know what it is, but it's in some units. And lambda 1 is the price in dollars per that unit. And so if this were 0, lambda 1 f1 would be 0, and there'd be no payment either way. But notice also that if f is positive, it would cost you. So it costs you to have positive f. Now, in the original semantics, the cost of having positive f1 is very simple. It's plus infinity. So in this, with this Lagrangian here, the cost is actually, it's linear. It's not something that goes from 0 to infinity. Okay, and these are called dual variables for reasons that will become clear later, or they're called Lagrange multipliers. And we'll call them lambda for the inequalities, nu for the equalities. Okay, so this is simply the Lagrangian. Now the Lagrange dual function is this. It says it's a function only of lambda and nu. And it says you should minimize over x the Lagrangian of x lambda nu. And if you'd like to think of it this way, it's the infimum well, that's the Lagrangian. And one interpretation of it is very nice. It's this. You could say that's the optimal cost with the prices given by lambda I and nu I, right? So and some people make a big story about it. We'll see this later. But, they think of this as sort of a market solution or something like that, that instead of strictly enforcing fi less than 0, instead you simply set a price lambda I. And instead of saying oh, you know, hi of x should be 0. I'll just put a price nu I. And then this says that you should minimize x over this. And so this is the optimal cost under the prices or Lagrange multiplier vectors, you know, lambda and nu. Okay, very important fact about G. That's this. It is concave, even if the original problem is non-convex. And let's see why. Here's the Lagrangian here. And as a function of lambda and nu, it is affine, period. For any x, it's affine. Okay, now the infimum over any family of affine functions is concave. So, done, right? So, now of course it can be minus infinity for some lambda and nu. Okay, it's an infimum. Of course it can be unbounded. Okay, now here's something that's going to be kind of obvious. It's going to lead to really interesting results, though. It's this. Suppose I told you that the Lagrange multipliers associated with inequality constraints are non-negative. Then the claim is the dual function evaluated at lambda and nu is a lower bound on p star. That's the optimal value of the original problem. Okay? Well, let's look at the proof. It's embarrassingly simple. It just says this. It says, suppose x tilde is any feasible point, and let's assume that the Lagrange multipliers associated with the inequality constraints are non-negative. That's here. Then it says the following. F0 of x, that's bigger than this, and I'll explain why in a minute. And this thing, I mean, by definition, if you minimize over x, if that's smaller than this value, but that's g. And this one here, this one follows from the most embarrassingly simple thing. It says the following. It says, take f0 of x, and suppose these are non-negative. If x is feasible, these are less than or equal to 0. And now we're going to use the deep mathematical result that the product of a non-negative number and a non-positive number is non-positive. We'll use another deep result that says that the sum of in this case, non-positive numbers is non-positive. So this whole thing here is less than or equal to 0. Now, it doesn't matter what the nu i's are, because if x is feasible, these are all 0, and the product of 0 and any number is 0. So this whole term is 0. And that says that whatever this is, when x, for any x, if x is feasible, then L of x lambda nu is less than f0 of x for any feasible. And if I infimize over x, I get this. Okay? So what this says is actually really interesting. It says this dual function, whatever it is, you can think of it as providing a parameterized lower bound on the optimal value of the problem, right? And it's parameterized by lambda and nu. Now, they could all be crappy lower bounds. For example, you could plug in lambda and nu, and g of lambda nu could be minus infinity. That's the universal lower bound. In other words, I don't have to know anything about your problem to say minus infinity is a lower bound. It's the completely and utterly uninformative lower bound. So you get lower bounds, and they're parameterized by lambda and nu. Okay? But by the way, that alone is quite interesting. By the way, one thing that you'd be tempted to do immediately is this. If I have a lower bound that's parameterized by some parameters, you should have the urge to change those parameters so as to maximize the lower bound, because as you maximize the lower bound, it becomes better, right? If I tell you here's a lower bound that's minus 12, if I can get another lower bound that's minus 10.5, that's better. So you should want to maximize the lower bound. That's quite interesting, because guess what? That function is concave. Maximizing the lower bound is going to be a convex optimization problem, right? So that's very interesting. Okay, let's look at some examples. Let's minimize x transpose x subject to ax equals b. Well, the Lagrangian is we take the objective, and to that we add nu transpose times ax minus b. That's the residual. And what we're going to do is we're going to minimize that over x. That's easy enough. It's, you can work out what the solution, I mean, you just take the gradient and set it equal to 0, and you get that. And you plug that in to this Lagrangian here, and you get the following. You get that. It is a negative, it is a concave quadratic function. That's what it is. Okay? I mean, by the way, it had to be concave because the dual function is always concave, but here we see it explicitly. And that says the following. This says, if you pick if you want to solve this problem, this says it's the least norm squared solution of Ax equals b. That says if you pick any value of any vector at all, any vector, and you evaluate this quadratic function here, that number is bigger than, is a lower bound on the optimal value here. Okay? Now, that's not so useful here because we can solve this problem exactly. Well, that's not entirely true. I'll give you an example. When x has size, let's say 100 million, this could actually be a challenge to solve, and you might use some kind of iterative method. And the iterative method, after some number of iterations, you'd have an x. And if you're lucky, you'd have Ax equals b, and you could look at the value of this. And suppose you find that that's 7.1. Let's just say, okay? Now, if you're lucky enough to be able to identify a nu, evaluate this number, and find out that the value of that, if that number evaluates to 7.0, you are super lucky. Because now you've shown you have an x that achieves an objective value 7.1, but your nu is a certificate proving that the best x has to have a value of this worse than 7.0. And that says you're pretty close to optimum, and you can quit with confidence, right? You can quit saying that at worst you're 0.1 optimal, suboptimal. We'll talk about these ideas later, but I'm just saying this has practical applications like immediately. By the way, you could ask a reasonable question. How would you choose this nu? Great question. Of course, it's a lower bound no matter what nu you pick, but if you pick a crappy nu, you're going to get a crappy lower bound. So we're going to answer those questions as we move on. But for now, it's just a lower bound, depends on nu. Any vector nu you plug in and evaluate that, you get a lower bound. Let's look at LP. I want to minimize C transpose X subject to X equals B and X non-negative. So here's the Lagrangian. It's the objective plus I take a nu transpose, that's this dual vector, times AX minus B. And here I'm going to write this X bigger than or equal to 0 as this thing, minus X is less than 0. And so I get minus lambda transpose X. That's the Lagrange multiplier term. And so I get this, and you look at that Lagrangian, and it's affine in X. Well, of course, it's going to be affine because every function involved in a linear program is affine. It's an affine objective, affine inequality constraints, and all you do in Lagrange, forming a Lagrangian, is you form a weighted linear combination of the objective and the constraints. So you get something that's affine. And now you're asked to minimize an affine function. Well, that's actually quite easy to do, right? If you minimize an affine function, basically, for most cases, you just get minus infinity. If this vector here is non-zero, I can make this thing as small as I like. I just go in the direction this vector, negative, and multiply by a big number. I get, this is unbounded below. So if I take the infimum of this affine function, I get minus infinity, almost always, except if this thing here is 0. If that's 0, L is quite boring. It's constant. It's minus B transpose nu. So I get a weird function G. It looks like this. It's minus B transpose nu, if this holds. Otherwise, it's minus infinity. So what it says is I have a parameterized lower bound on the optimal value of this LP. It's parameterized by a vector nu and lambda. Now, if nu and lambda don't satisfy this equality constraint, then my lower bound is minus infinity, which is a completely uninformative lower bound. But if they satisfy this constraint, I can announce minus B transpose nu is a lower bound on this LP, right? So, for example, if I were lucky enough to find a nu and a lambda that satisfies this, and minus B transpose nu equals C transpose X, I would be done, and I would absolutely know it. I'd know it because I have a point that's feasible, achieves a certain objective value, and I have a lower bound showing that that objective value is optimal, right? So I'm getting ahead of myself, but this is where we're going with all this, the practical applications. So what does this mean? To say there exists a lambda for which A transpose nu minus lambda plus C is 0, that's the same as saying A transpose nu plus C is bigger than or equal to 0, because you just take the negative of that to be lambda. Sorry, that's equal to lambda. And so what it says is this. It says that if you have this LP here, and it says that if you find a vector nu that satisfies A transpose nu plus C is bigger than or equal to 0. Now, at the moment, we don't know how to find such a vector. We have no idea. We're going to see later how to find such a vector. But right now, we don't concern ourselves with how we find it. If you find a vector nu for which A transpose nu plus C is bigger than or equal to 0, then this number, minus B transpose nu, is a lower bound on the optimal value of that standard form LP. Okay? So that's the idea. And, you know, this is, we derived it through Lagrange duality. You know, it's not hard to show. You could show this directly, although if you didn't know about Lagrange duality, you might not have guessed such a thing. Okay. Let's look at equality constrained norm minimization. We already looked at one that was kind of like this, but not quite because we squared it. So let's minimize norm x. Norm is a generic norm subject to ax equals b. Well, the dual function is the infimum of the norm of x minus nu transpose ax minus b. That's this here. And here, we're going to infimize this over x. Now, here, that's the norm minus a linear function. Well, the norm minus a linear function, we have to see if that's, we have to minimize over x. That's a homogeneous function. So the only possible things that can happen is you either get 0 or you get minus infinity when I minimize. And in fact, I get 0 if and only if the dual norm of A transpose nu is less than or equal to 1. So that's this term. Okay? All right. So now I have a beautiful lower bound property. It says if you want to do general norm minimization with equality constraints, it says the following. If you're solving that problem or whatever you care about, it says if you can find a vector nu for which A transpose nu in dual norm is less than 1, that tells you that B transpose nu is a lower bound on the optimal value here. Okay? So I think you can see here what we're doing is we're generating parameterized lower bounds on the optimal value of an optimization problem. I mean, that's kind of what this is. We have not yet said anything about how do you optimize that parameter, anything else like that. How tight is this lower bound? We're going to get to all these things, but for the moment, that's the correct way to think of this, what we've done of Lagrange duality so far. Okay. Now, our last example of this is actually one where it's quite interesting. It's a non-convex problem. So let's take a look at that. Here it is. You'll recall the partitioning, two-way partitioning problem is I have n items, and I'm going to partition them into two groups, right? And I'm going to encode the partitioning by taking a vector x on Rn, and the entries are either going to be +1 or -1. +1 means one group, -1 means the other, right? So a +-1 vector corresponds to a partitioning of these x into two groups. And I have a matrix W that tells you how irritating it is for xi and xj to be in the same partition, and that's given by wij. And so this is, so wij, I guess you could say, is that's how much, let's say person I hates person j, let's say. Dislikes, let's not use hate, dislikes person j. That would be for a constraint. So dislikes. And so this says, and then if they're in the same partition, right, then, this is, of course, some xi, xj, wij. And if they're in the same partition, then they're both either +1 or -1, and you add wij. If they're in different partitions, xi and xj, the product is -1, and you actually subtract wij, right? So this says something like, partition into two groups in the most harmonious way. Okay? Now, that problem, you may know, we've already seen it, that's actually NP hard. So that is as hard as many other combinatorial optimization problems. No one knows how to solve this thing exactly and quickly. So it's a complicated problem. By the way, there are many, many methods to solve this approximately. And in fact, we're going to see some momentarily. And it's a problem that comes up all the time, right? So, for example, well, okay, we'll move on. So that's a non-convex function because these constraints are not remotely convex, right? That's a quadratic equality constraint. By the way, this relaxation, that's convex. And that's a very famous relaxation of this problem, and I think we've seen it before. However, what we're going to do now is we're going to take this. By the way, there's also no reason to believe that W, while it's symmetric, there's no reason to believe it's positive semi-definite. Okay, so here's what we're going to do. We're simply going to follow the rules. You take F0, and to that you add sum of nu I times, these are hi of x, and that's these quadratics. And if you look at what this is, it's a quadratic plus a constant in x. Well, it's a quadratic. How do you minimize a quadratic? That's very simple. Minimum of a quadratic is either minus infinity if it's got a negative eigenvalue, or it's 0 if it's positive semi-definite. So what you get is the dual function is either minus infinity, or if this matrix is positive semi-definite, the best x you can do, I mean the x that minimizes this is x equals 0, and then you just get this thing left over, you get that. And that happens if that's true. And that says, we have the following statement. If you can find a nu such that W plus diag of nu is bigger than or equal to 0, then minus 1 transpose nu is a lower bound on P star. Okay? That's incredible. It's quite sophisticated. It says that, by the way, that's an LMI in nu. That's a linear matrix inequality. It says that if this matrix inequality holds, then you get a lower bound. Okay? It's quite interesting. So for example, here's one. You take nu is minus lambda min of W times all of 1s, and you get a very famous bound for this problem, which is this. The optimal value is bigger than or equal to n times lambda min of W. Okay? And I'm going to show you another way to derive that. Another way to derive this inequality, very famous inequality. By the way, it suggests a method for approximately solving this problem, which is actually called, well, in this case, it's spectral partitioning. But let me derive this another method that's maybe simpler than Lagrange duality. It goes like this. You want to solve this problem. If you cannot, it's too hard. So you look at it and you say, you know what though, if xi squared is 1, I'll tell you one thing I know for sure. Sum xi squared is n, because each of the numbers is 1, okay? And that says, so these n inequalities imply that inequality, okay? That's one way to say it. Or if you like to think geometrically, these inequalities say that xi sits on the vertex, it's on a vertex of a hypercube. So there's a cube in Rn with entry, the vertices there are Boolean vectors, right? That's the hypercube. Then, interestingly, this is the sphere that covers the hypercube. Okay? So you can think of it as a relaxation. It says that if you're on a vertex of the hypercube, you're in the sphere. But you know what? I know how to minimize an arbitrary quadratic form, x transpose wx, subject to this, because it's simple. That's one of these non-convex problems we can actually solve. If I say what's the minimum of a quadratic form, subject to the norm being 1, the answer is it's lambda min of W. And you take x, by the way, to be an eigenvector associated with the minimum eigenvalue. And so here, the sum of the square, the norm squared is n. So that scales everything up by n, and you get this bound. You get the same bound. It's a beautiful bound. By the way, it also suggests a good idea for x, and I'll tell you what it is right now. You compute the eigenvector of W associated with its minimum eigenvalue. That's the first step. And you get, and let's call that vector v. Then you simply take xi is the sign of v. Done, right? That does quite well. When you think of this as a partitioning problem, this is called spectral partitioning in this case. Well, that's one name for it, although that name is used to refer to something similar but not the same, but that's the idea. So the point here, let me sum up what the point of this is. This is a hard problem, right? If W is 1,000 by 1,000, I don't know what if I give you a 1,000 by 1,000 sparse W and I say solve the two-way partitioning problem, it's not unreasonable to say the following. You can't solve that problem. You can't tell me what the global minimum is. Okay? What this says is the following. It says you can get a lower bound. You have to exhibit a vector nu, check that this matrix here is positive semi-definite. If it is, -1 transpose nu is a lower bound on that optimal value. Now, in this case, this is exceedingly valuable, because, for example, you could do spectral partitioning. You could start with this one, and you could observe that it gets good results. By the way, after you do this, you could do something like a greedy heuristic. I would do it. Once you find this bit vector, Boolean vector, all the x's are plus minus 1 here, why would you not do the following? I would cycle through x, and for each xi, I would flip it and see if the objective gets better. Most of the time it doesn't, but if it ever gets better, I take it, and that's my new x. And I keep running through my data until this stops. And then when I stop, I think that's called something like 1 opt in combinatorial optimization. What that means is I can't change one of my variables and improve the objective. Okay? So that's 1 opt. It just means it's a kind of local optimality. It doesn't mean you're at the optimal point. So the point is the method I just mentioned, spectral partitioning followed by a local optimization, a greedy local optimization, I can implement that for a matrix W which is 50,000 by 50,000. Actually, I can scale it as big as you want, and people do. And you will get exceedingly good partitions. Okay? The question will be, how do you know it's good? And the answer might be, although I haven't said yet how you'd find it, you'd do the following. You would exhibit a nu. Demonstrate that W plus diag of nu is bigger than or equal to 0. And if that's true, you can simply assert that the optimal value of this problem, whatever it may be, which no one knows, it's bigger than this. And if that number is close to this number that you got by your heuristic method, it's your lucky day, because now you know that although your method was heuristic, on that problem instance, you were lucky and you actually solved the problem either exactly or to some precision, right? So that's the idea. Okay. Now, in general, there's a strong connection between the Lagrange dual and the idea of a conjugate. So let's just see how that works. If you minimize F0, subject to AX less than B linear equality and inequality constraints, you form the Lagrangian, but because all the constraints involve linear functions, you're adding a linear function to an objective, to a function, and you're minimizing. But we have a name for that. That's called the conjugate function, right? Because the conjugate function minimizes, it minimizes f of x minus a linear function of x, right? I mean, okay, it maximizes y transpose x minus f of x. It's the same thing. So that's the conjugate. And what that says is there's just a little formula for the dual function of a problem with linear equality constraints. It's a very simple formula. It's just this. It's minus F0 star of minus A transpose nu minus C transpose nu, A transpose lambda, and then with this linear part. Now, you have to be very careful turning this around with all the minus signs and so on, but this is probably correct. And if it's not, then it's close with one minus sign or something off, but that's it. So don't recommend this because it's better. I mean, I derive dual functions by hand every time because it's good exercise and it's just as hard to use some formula like this one. But let's do one. Let's do entropy maximization. So here I want to minimize negative entropy subject to some equality and inequality constraints. Well, that's the dual, the conjugate of that is actually sum of exponentials. That's beautiful because it'll allow me to get the conjugate like immediately. And so the original problem I solve is linearly constrained with inequalities and equalities, entropy maximization. I can get a dual function and it's going to involve exponentials. That's quite interesting. We get to what's called the dual problem. Now, we've been hinting at this for a while and it kind of makes sense. If you think of G of lambda and nu as a lower bound on P star, right? If it looks like if that's your interest and interpretation of what the dual function is, lambda and nu are parameters, then, and you're interested in getting a lower bound on p star, then obviously you'd be interested in getting the best lower bound. So that's the so-called Lagrange dual problem. It says maximize this lower bound, g of lambda nu, subject to the lambda is bigger than or equal to 0, and you need that constraint there because otherwise that's not a lower bound. Okay? So, and you can interpret this problem this way. It's finding the best lower bound based on Lagrange duality. By the way, there's no reason for you to believe at the moment that it's good. I mean, but it's just the best lower bound you can find by Lagrange duality. We're going to call the optimal value of this d star, and we obviously have p star is bigger than or equal to d star, right? So we'll say more about these two numbers shortly. Okay. And a lot of times people will do a little bit of a transformation, right? So for example, if you have an LP, you form its dual, and its dual is really this. It's maximized g of lambda nu subject to lambda bigger than or equal to 0. But remember, the g is most of the time minus infinity. So if you make those implicit constraints explicit, you get something that looks like that, right? And so although it's not quite right to say, this is, people would say this is the Lagrange dual of that problem, okay? And by the way, we can interpret it in a beautiful way. Someone says, what does that mean? And you'd say, oh, I can tell you what it means. It says, if you find a point, nu, that's feasible for this problem, it says this objective value is a lower bound on the optimal value of this problem. That's what that says. It's quite interesting, right? Then they say, well, what is this optimization problem? You say, oh, simple. That says, please find the best lower bound on this problem obtained by this method, which is Lagrange duality. Now, you always have d star is less than p star, always. Oh, notice that in principle, d star is computable. D star is computable because you're maximizing a concave function. Now, you can't always maximize a concave function. You have to be able to evaluate it and things like that. And so I want to be careful and not assert that it always works, but in many cases you can. Okay. Now what this allows you to do is you can find non-trivial lower bounds for hard, difficult problems. So for example, let's go back to that two-way partitioning problem. It says if I solve this problem, that's a semi-definite program. That gives you a lower bound for the two-way partitioning problem. Okay? And it will not be equal to p star, but you'll get a number d star, which is less than p star, and it's often a very good lower bound. Not always, but it's often quite good. We'll maybe say more about that later. Now, strong duality says, what happens when d star is p star? Now, what does that mean? What that says is that the lower bound on p star obtained by Lagrange duality is tight. It says you had a parameterized lower bound, but if you adjust the parameters just right, the lower bound goes right up to the actual optimal value. Okay? And in fact, by the way, people call p star minus d star the duality gap. We'll see more about this later, but that's called the duality gap. And so strong duality says there is no duality gap. Okay? Now, by the way, for a non-convex problem like this, there's a gap. There's a duality gap. And this one there is. There had to be. If there was no gap in this problem, then this would constitute a proof that p equals np. Not that that's impossible, but it just doesn't happen to be the case at this moment or when this was first observed. Okay. Now, in general, there's no reason to believe that d star is p star. I mean, there's no reason to believe that. But for convex problems, it usually holds. Not always, right? And you have to add extra conditions to the problem to make sure that you get d star equals p star. And these are called constraint qualifications. That's a historical term people use. And you add those. You say if the original problem is convex and blah, 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 then d star equals p star. Okay. So the sledgehammer of constraint qualifications is Slater's constraint. It's the only one we're going to look at. Well, we'll look at a minor variation on it. I mean, there's entire courses, whole semester-long courses that do nothing but look at constraint qualifications. The whole course is a big glorified study of when do you get P star equals D star, and that's very interesting mathematics. But the sledgehammer is Slater's constraint, and it's real simple. It says this. It says that if you take this if that problem is convex, and if there exists a strictly feasible point, that merely means there's an x that satisfies x equals b, and these inequalities hold strictly, right? If there is such a point, that says Slater's constraint qualification holds, and in that case, P star equals D star, period. Okay? Now, it suggests other things as well, but okay. And by the way, there's tons of other types of constraint qualifications. They depend on things being affine, non-affine, various things being bounded. It goes on and on and on, but that's the idea. Oh, and I should say, there's a variation on this that's actually useful, and it says the following. It says that you can exempt linear inequalities from the requirement of Slater. So in other words, if the only inequalities that have to hold strictly are the nonlinear ones, and that's like a Slater, that's a sharpened Slater's condition, and that one is quite useful. Let's look at inequality form LP. There's the primal, there's the dual problem, right here, and okay, now the question is whether or not if I solve this problem, do I get the same objective value as solving this one? And Slater's condition says the following. It says there should be a strictly feasible point here. There should be an x with ax tilde is strictly less than b. Okay? Now, in fact, you can say more here. The strengthened Slater's inequality says all these inequalities are linear. Therefore, they are exempted from the strictness requirement, and from the strengthened version, right? From the strengthened Slater's condition, the only thing you have to satisfy is that. And that says, that's the same as saying the problem is feasible. So the strengthened Slater's condition says, for this inequality form LP, if it is feasible, then P star equals D star. Okay? Now, it turns out you get P star equals D star even in cases when something is infeasible or unbounded. But it can turn out for an inequality LP, there's one pathology, and you can actually have P star is plus infinity and D star is minus infinity. That can occur. But all these other ones cannot, right? So, okay. So that's that's duality theory, the summary level for LP. Let's look at QP. Let's minimize this quadratic function. Let's make it strictly convex. That's to make minimizing the Lagrangian easy, subject to linear inequalities. Here we form the Lagrangian. That's this thing. So I take this affine function and I rewrite it. I augment it, the objective with that, and I minimize. That's a quadratic function. And I can work out exactly what it is. I just set the derivative equal to 0. I get 2px plus lambda, and I solve it. And I get that, which is a concave quadratic. And so the dual problem looks like that. Okay? Now Slater's condition says, the basic Slater says you have to have something that's a polyhedron. This says there has to be a point in the interior of the polyhedron. If I strengthen this from the strong version of Slater's condition, it's simply this. It says it has to be feasible. So that says that if it's feasible, you get P star equals D star. But in fact, in this case, it's always the case. You always get P star equals D star, by the way, including the case when these two numbers are plus or minus infinity. Okay? So in other words, the following is true. If the optimal value of this is plus infinity, right, that would occur if, for example, well, not if, for example, that occurs if and only if ax less than or equal to b is infeasible, that set of linear inequalities, right? That is if and only if the optimal value of this problem is plus infinity. That's interesting. So that says this dual problem is unbounded above when this primal problem is infeasible. And that's super cool because what does it mean to say the dual problem is unbounded above? It says that you can make the dual objective as large as you like. But the dual objective is always a lower bound on the optimal value. If I can make that as large as I like, you have to have P star equals infinity. So it's got to be. And in this case, you get perfect, strong duality all the time. Okay. I'm going to mention one more. I'm not going to go into the details. This is handled in one of the appendices in the book in much more detail. This is an advanced topic. But it's an interesting one, so I'll just talk about it. You can have strong duality, P star equals D star, in cases where the problem is not convex. So this can actually occur. Now, if the dual problem is solvable, which generally it is, right, then it says the original problem can actually be solved. I mean, this is all very rough, but the original problem can be solved by convex optimization. It's tractable. That's very interesting. And by the way, the general case there is the following. Any optimization problem involving exactly two quadratic functions, so minimize a quadratic function subject to quadratic inequality or something like that, every such problem can be solved exactly, okay? And convex or not. I mean, there's many ways to understand why that's true, but one is to understand the following. It says that for all such problems, the dual problem is actually an SDP. And you can prove using, in fact, you have to use the structure of the problem, some algebraic geometry, something like that, that basically says there's zero duality gap. And I should say a little bit about this, what the connection is to things that we've seen. If you think about what are all the problems that people can actually solve, right? Well, a huge number of them are convex, but some are not. And there's some real obvious ones just glaring out there. I mean, here's one. If I walk up to you and I say, well, how do you solve this problem? Like, maximize x transpose px subject to, say, norm x2 equals 1. How do you solve that? Well, we know the answer. I mean, you take the largest eigenvalue of p, and x is the eigenvector associated with that. Fine. This thing is not close to, I mean, that's not convex, right? Because p could be anything. It can have, p, if p is negative semi-definite or something, then this is a convex problem. But other than that, this works always. P can be positive definite. It doesn't make any difference at all. And that equality constraint sure is not convex, right? I mean, you can relax it to this and it becomes convex, right? But in general, that's not convex, right? So, and this is, of course, this is the basis of all sorts of things. This is the basis of PCA, principal component analysis, singular value decomposition. These are used everywhere, all the time, all sorts of cool stuff, okay? And these are non-convex problems. So if someone asks you, what are you doing? I'm studying convex optimization. Why? Because a lot of problems are convex. If they say, are all problems convex? You'd say, absolutely not. And ones that are widely used that are not convex, examples would be PCA and SVD. But what this says is there's at least a weird technical argument you can make where you'd argue that PCA and SVD they're solvable because they're convex. I mean, I don't believe that. That's weird. But there is a connection. You can solve them using convex optimization, and it's this. Let's look at this, return to this specific example, which is a special case, by the way, of this, sort of. So the dual function here is you take the objective, and to that you add this inequality with a lambda, and you get that. You get a quadratic function, but we can minimize a quadratic function, right? If it has a negative eigenvalue, it's minus infinity. Otherwise, you work out what it is, and you end up with a dual problem that looks like this, and it's actually easiest to write it as an SDP. It's cleaner. It says maximize minus t minus lambda subject to this LMI, okay? Now, that is an SDP. We can solve this thing. Here's what's interesting. The gap, the optimal value of this problem is actually always exactly equal to the optimal value of that one. This one is a non-convex problem. This one is convex and tractable, right? And that says we have a way to solve this problem. Now, in some special cases, you already knew that. I mean, you don't, and obviously when we teach people linear algebra and you learn about things like PCA the first time, you don't tell students at that point about things like, SDP duality and things like that. You just say, look, we can compute the eigenvectors or something. That's the solution. But it is interesting that there is this connection. Okay, I think we're going to do one last thing we're going to do is get a geometric interpretation of what P star is, what D star, and in fact what a duality gap looks like. So here's what it is. We're going to do it for a super duper simple problem with one objective, F0, one constraint, F1 of x is less than 0. And we're going to write down this in the following plane. This is going to be the constraint function. That's F1, right? This axis is going to be F0. And so your goal, G, is going to be the set of all possible pairs of values of F1, F0. And so your job is to focus only on ones where the first component is less than or equal to 0, and among them, find the lowest value there. So in other words, we should take this picture. We should focus only on the left, because these are feasible points. And then among those points, that gives you this little thing that goes down like this, the little nose-like thing. And then it says, go as low as you can here. And the answer is you go right down there, and then that's P star. Okay? So now you see what P star is. That's what it is. All right. So, I mean, here's for example, that's a point that has a lower value of F0. But it's infeasible, because this means the fact that it's to the right says it's F1 is positive, and therefore it's infeasible. Okay? So this is the picture. This picture right here, this little point here is going to be P star. Okay. Now let's look at Lagrange duality, because on the same plot we can actually look at the Lagrange dual problem and see what happens. So on the Lagrange dual says take what you do is you take lambda 1, and you take the inner product of lambda 1 with this vector and minimize it. And the minimum value of that's exactly G of lambda. And so what it says is you take you take a vector like this whose slope is, in this case, because you're multiplying lambda 1, that's the first thing, the slope is exactly lambda or negative lambda, and we minimize it. Okay? And so what that says is I set the slope, and the slope then we find in this whole set here, we find the closest point. So if lambda is big enough, you get this value. And as you crank it up, you would get things like up here, right? And you could see that this would go like this, turn. It would actually, at one point, it's supported at 2 points there, and then it would keep rotating that way. And it turns out in that picture, where that intersects this axis here, that's D star exactly. Okay? And so that says, for example, if I take lambda that's totally inappropriate, like this one here, that's got a lambda. This continues down there, and way down here, they cross. And that crossing value, that's a lower bound on P star. Well, indeed it is. It's a really crappy one. As I take lambda and change it so I move like this, that lower bound gets better and better and better until right when I'm here, right, I now hit this part, and when I keep rotating, which is changing lambda, in this case I am turning lambda down, I keep rotating, and now the dual objective value, G of lambda, goes down now. And it reached its maximum right when it was touching these two parts in its D star. And so now you can see exactly what the duality gap is, right? The duality gap is exactly the following. It's the gap between this thing that went over horizontally here, and then the best line that was tangent to this set G. And what you get there is this point, and this gives you the duality gap is this distance here. And in fact, this picture is enough to tell you almost everything. So you can see it's not true that G is convex when F0 and F1 are convex. What is true is the lower left-facing face of G, that's convex. And so you can see here that the reason we got a duality gap here is clear. It's because we were able to sort of hide the solution inside a dent in this set G. If G is convex, or at least its lower left face is convex, you can't hide. There's always a supporting hyperplane that goes there. So that's this picture, once you understand it all, it explains pretty much why for convex optimization problems you generically have zero duality gap. The truth is you can also understand Slater's condition using this graph as well. Okay, so how do you do that next step? That's simple. What you do is we replace that G with its epigraph. And what we do is we simply replace things. It's these values plus everything up and to the right. Now, that set is convex if F1 and F0 are convex. That set is convex. Okay? And nothing changes if you do this. And then strong duality basically is the following. It says if at this point there is a non-vertical supporting hyperplane, then strong duality holds. And Slater's condition says the following. It says A is convex, and it also says, not only that A is convex, but it says the very important part, which is this, which is that A penetrates over to the left, and therefore, at this point here, it has a non-vertical supporting hyperplane, which looks like that. And sure enough, that slope is the optimal Lagrange multiplier, lambda star. And then in this case, you get P star equals D star. So that's the picture that's what happens when you apply. That's the analysis that even explains the geometry of the Slater condition. The next topic is this idea of complementary slackness. And so we'll start assuming the following. Assume X star is primal optimal, and we have dual optimal variables, lambda star and nu star. Now what that means is that F0 of X star, that is the objective attained by X star, is equal to G of lambda star nu star. And that's the lower bound that you get from Lagrange duality from the dual variables lambda star and nu star. And of course, we assume here that X star is primal feasible, lambda star and nu star have to be dual feasible. And of course, if we have this equality, that's the end of the story. We know for sure X star is optimal for the primal problem. And we also know, by the way, that lambda star and nu star are optimal for the dual problem. Okay, so now assuming that you have a primal dual pair, I'll call it a pair because it's a pair of a primal variable and a set of dual variables. If I have a primal dual pair, let's see what it means. Well, this dual function value, that's by definition. That's the infimum over x of this thing. Well, the infimum over x is certainly less than if I plug in any particular value of x. So I'm going to plug in x star, my primal optimal point. And I say that this thing is, of course, less than that. And in fact, you get equality here if and only if x star also minimizes the Lagrangian. We'll come back to that in a bit. So right now, I'll just say that's less than or equal to that. But now we're going to observe the following. We're going to observe that x star is feasible. Therefore, the fi's are less than or equal to 0. The lambda i's feasible too. So lambda I star has to be bigger than or equal to 0. And therefore, each of these numbers is less than or equal to 0. The sum is less than or equal to 0. This thing is less than or equal to 0. And this term here is 0. Why? Because if x is feasible, hi of x star is 0. And therefore, this is just 0. That just goes away. And we see that this is f0 of x star plus something less than or equal to 0. And that's less than or equal to that. And now we have a chain. And we see that, in fact, these must have been equalities here. These must have been equalities. Okay, so if they're equalities, now we go back and see what it means. Well, it can mean the only place means actually two things, and we get some interesting things. The first is it says x star minimizes the Lagrangian. Okay, that says the Lagrangian evaluated with the dual variables, the optimal ones, right? So that says if you have dual optimal lambda star nu star, then any optimal x minimizes the Lagrangian. It has to be because the only argument I used here was that x was optimal and that lambda star nu star was optimal. Okay, that's the first one. And that's what would give you equality here. Now, to get equality here, this term must be 0. But it's a sum of terms that are less than or equal to 0. If a sum of things less than or equal to 0 is 0, every single one is equal to 0. And in that case, yes, you get something very interesting. It says that the individual products, lambda I star and fi star of x, fi of x star, those are 0. And that's called complementary slackness. That's the name for that condition. And there's several ways to say it. Well, it basically says that you have the inequality. You have two inequalities here. You have lambda I bigger than or equal to 0, and you have fi of x less than 0. And to say that one of these inequalities is slack is the same as saying that it holds strictly. And so what it says is that if one of these holds with some slack, the other must hold without slack. You can't have slack on both. That's basically what this is saying. In fact, the product has to be 0. So another way to say it is, if the optimal Lagrange multiplier is positive, strictly positive, then that constraint absolutely must be tight. That's what it says. Okay? Conversely, if a constraint, well, it's not conversely, it's kind of the same statement. It says if a constraint is slack, if there's an optimal point where the ith constraint is slack, that's what this less than or equal to 0, less strictly less than 0 means. That says the associated optimal Lagrange multiplier must be 0. Okay? So now the meaning, by the way, for all of these things, it's actually quite an interesting statement, because this holds for any optimal x and any optimal lambda and nu. And what that says is if there's just a unique optimal x star, unique optimal lambda star, nu star, it just says these things hold. But other than that, it holds actually for any optimal x, any optimal lambda star and nu star. Okay. So this leads us straight to something called the KKT conditions. It's an interesting story behind this. Kuhn and Tucker worked out these conditions. And then several years later, substantially long time later, and in fact, you can look in old books and find these referred to as the Kuhn-Tucker conditions. And at some point, somebody did was poking around somewhere and found out that Karush had written a master's thesis at University of Chicago, completely unpublished, with essentially the same ideas in it. And Kuhn and Tucker were nice enough to prepend Karush's name to the results. So it's now the KKT conditions. Okay. So here I have a problem with differentiable Fi and Hi. Okay. So, and it says here are the KKT, the Karush-Kuhn-Tucker conditions. First of all, primal feasibility. You have to satisfy, x satisfies the inequalities and x satisfies the equality constraints. Okay. Dual inequality constraints, I should say. Lambda has to be bigger than or equal to 0. Complementary slackness. That says that here, whenever lambda I is positive, Fi is 0. That's one way to say it. You could say it the other way around. You could say that whenever Fi is negative, you must have lambda I 0. And the fourth condition is that the gradient of the Lagrangian with respect to x vanishes, right? So that is the gradient with respect to x of L, and that's given by the gradient of F0 plus some lambda I gradient Fi of x plus some this nu I times the gradient of Hi of x equals 0. Okay, so these conditions altogether, that's called the KKT conditions. And what we saw on the previous slide here is the following, that if the problem is convex and x, lambda, and nu are optimal, which really means x is primal optimal, lambda, nu is dual optimal. If that's the case, then these four conditions hold, right? This holds because we saw here that whenever this holds, when you have zero duality gap, x star must minimize the Lagrangian here. This is a convex function, right? And if F0, Fi, and Hi are differentiable, the idea that x0 star minimizes this says that if I plug in x0 star here and take the gradient, I better get 0, right? So that recovers this condition. So what that says is for a convex optimization problem, if x, lambda, nu are optimal, KKT conditions hold. Now the converse is also true. You have to be kind of careful about this, but the converse says this. If I have 3 points, x tilde, lambda tilde, nu tilde, and they satisfy the KKT conditions, and it's a convex problem, then they're optimal. And you have to go back and check various things. From complementary slackness, you can show the following, that f0 of x tilde is L of x tilde lambda tilde nu tilde. That's easy because, well, the only difference here are the sum lambda I tilde times fi of x tilde, but that product is 0. That's by our assumption on complementary slackness, and the other one holds too because of primal feasibility of the equality constraints. So you get this. From the fourth condition, that says that it says that the gradient of the Lagrangian evaluated with dual variables lambda tilde nu tilde, the gradient with respect to x vanishes at x tilde, but it's a convex function, the Lagrangian with respect to x, and if its gradient is 0, you must have minimized it. So that tells us that x tilde minimizes that, and that tells you that if x tilde minimizes it, then this thing is equal to g, the lower bound. And we are now done because we've shown that g of lambda tilde, which is a lower bound on the optimal value, is equal to f0 of x tilde, where x tilde is primal feasible, and that's the end of the story. X tilde is primal optimal. And by the way, lambda tilde and nu tilde are dual optimal. So, okay, so that is the argument for this. So roughly speaking, you can say that Slater's condition, the KKT conditions are the necessary and sufficient conditions for optimality for a convex optimization problem with equality and inequality constraints. Now, it assumes that the FI, the objective, and the constraint functions are all differentiable, right? And it's a nice extension of the standard optimality condition for an unconstrained problem. It's just the gradient is 0, right? So that's the idea. Okay. Now, in a few cases, the KKT conditions allow you to solve a problem. Now, they're not the most interesting problems, and there's other ways we can think of them, but they do give you, they do come up, and they're interesting to look at. So here's an example. This one comes up in, for example, wireless communications. What you've got is you want to minimize the sum of log xi plus alpha i. Alpha i are a bunch of positive constants that you're given. And the x's have to be bigger than or equal to 0, and they have to sum to 1. Right? So this is they could sum to any other number. This is good enough. And so that's the question, right, is how do you solve this? Oh, by the way, if you're curious what these things are, x could be the power in a channel, and you want to allocate the power across a bunch of channels, and the alpha has to do with the signal to noise, the noise level in that channel, right? And this says, how do you optimize the maximum, how do you get the maximum bit rate by allocating power to your different channels? Okay. All right. Well, let's just write down the KKT conditions. Write down the KKT conditions. You need a lambda and a nu. There's a lambda associated with the inequality constraint, and a nu, a single scalar nu associated with this constraint here. Okay. So x is optimal if and only if it's non-negative, it sums to 1. That's primal feasibility. And there exists a vector lambda in Rn, which is non-negative, right? And a single number, nu. And they have to have the following properties. This is simply writing down the partial derivative of the Lagrangian with respect to, this is simply the partial derivative of the Lagrangian with respect to x. And you get the following condition, well, you get this condition here, right? This is complementary slackness, and that is the gradient of the Lagrangian with respect to x is 0. All right. Now, we stare at these things, and we can work various things out. Let's see. If I told you that if, for example, well, we can work out, the conditions actually just depend on this one, right? If xi is 0 here, then we get 1 over alpha I plus lambda I equals nu. And so we can work out what lambda I is, and lambda I would be nu minus 1 over alpha I. So that gives you alpha I. That gives you lambda I. Okay? On the other hand, when x is positive, you have to have lambda 0. And for those, if lambda is 0, again, we can get what x is. X is from this equation, x is 1 over nu minus alpha I. And the only thing that we haven't satisfied yet is this condition here. Oh, and we can work out what these two conditions are because it's going to depend on whether nu is less than 1 over alpha or bigger than 1 over alpha. That's the conditions under which you end up with something that satisfies this with alpha being bigger than or equal to, with using the fact the alphas are positive. Okay, so what that says is if you work out what these values are, it says we're going to determine nu from 1 transpose x, but if x has either this value or this value, it's this. It's the max of 0 and 1 over nu minus alpha I. And we simply have the sum of those is equal to 1. Okay? Now, you notice a couple of things here. We're going to adjust nu to make this true. Now, that can be done. Why? Because if I increase nu, this goes down, and therefore everything here goes down. And so the sum is monotone decreasing. If nu is gigantic, I get, if nu is extremely large, right, then this is max of 0. This is just 0. This left-hand side is 0, so you're way under 1. On the other hand, if nu is tiny, then 1 over lambda nu, 1 over nu is a very big number. You subtract alpha I, and this is a very big number, and you're way over 1. So you can simply use bisection. It's monotone. Okay, and there's a beautiful interpretation which gives the name of this method water filling. And the idea is something like this. You draw a profile of the alphas. So these are the alphas, right? This is I. That's I equals 1, 2, 3. That doesn't matter, of course. And then what happens is it says that you choose a value nu. That's right here. You write 1 over nu here. And then you imagine that you take this thing and you flood it to this level. Okay? So you flood it to this level. And what you do is this amount here, that is actually xi, right? So, and the idea is you take a total unit of one amount of water and you dump it on this thing, and when it all settles out, the sum of all these will be 1. Well, that's exactly what we have here. And the depth will be the correct value of xi. So you can see here that, for example, x3 is 0, right? So are these two, whatever they are, they're 0. And that's the idea. Okay, so this it's water filling. If you've taken a class on information theory, you have definitely seen this. Now, the last topic in duality that we're going to look at in standard duality before we look at other variations on it is this idea of perturbation and sensitivity analysis. This is extremely useful. It's also a very good way to think of it, and it has huge practical use. So let's see what it is. We start with an unperturbed problem. That's this one, okay? And it's dual. There's the dual. So the unperturbed problem says here are some constraints, inequality constraints, here's equality constraints. And what we're going to do now is we're going to perturb the problem. And let me explain what that means. We are going to change the right-hand side here from 0 to ui here, and in the equality constraints from 0 to vi, okay? Now, when you do this, I mean, these are just constants. They go over there, and you can figure out exactly how they affect the dual function. You get a new dual that's that. That's the new dual problem, okay? So, and what we're going to do is we're going to let p star of uv, that's going to be the optimal value of this perturbed problem as a function of u and v. Okay, so that's the idea. Now, we'll be able to show pretty quickly that's a convex problem. That's a convex function of u and v. And what we want to do is get some information about p star, u, and v. And first, before we do that, let me say a little bit about the interpretation of what it means. Here, let's concentrate not on the vi, which is actually hard to interpret, but let's look at let's concentrate on what ui means here. If ui here is equal to, let's say, 0.1, the question is, what does that mean? Well, if let's take it u1 is 0.1. If u1 is 0.1, it means precisely the following. It says that your original constraint was f1 of x had to be less than or equal to 0. f1 of x is basically, the idea is that 0 is right when you've reached some resource. And what it says that if you perturb it by making that 0.1, it says you've given about 0.1 more you've given 0.1 more units of resource to the first, whatever the first constraint handles, right? So you have more resources. Or you could say it's a relaxation because the feasible set is bigger. But whatever happens, I guarantee you this thing goes down, right? Because I give you if it's a circuit design problem and the first constraint expressed the power constraint, and I tell you I'm going to give you 0.1 more power, you better come up with a better design. Not a better design, but certainly you can come up, you shouldn't come up with a worse design, right? So that's what that is. So you would say that when ui is positive, you would say something like, I have loosened the ith inequality, ith constraint. On the other hand, if ui is negative, you have tightened the ith inequality. That's what that means. Tightening it means you've restricted the resources and so on. Now, by the way, if I tighten this problem, if I tighten a constraint, there's no reason to believe that this thing cannot go to plus infinity. I can tighten a constraint, and the whole problem becomes infeasible, and this number p star of uv will then be plus infinity. Okay? So, all right. So what we're interested in then, and one way to interpret what p star tells you how the optimal value changes when you tighten or loosen the inequality constraints, and you can interpret VI as a shift in inequality constraints. So that's what that is. Okay. Now, as a result here, it's actually quite easy to work out. You just simply apply weak duality to the perturbed problem, and you get the following. P star of u and v, that's the optimal value of the perturbed problem. It's at least as big as P star of 0, 0. That is the unperturbed problem, minus U transpose lambda star minus V transpose lambda star. And this holds for any lambda star, nu star that are dual optimal for the unperturbed problem. Okay? Now this is an inequality. It says, in fact, it says that when you perturb the problem, your results will be at least this bad. It's a bound on how good they could be, because this says if this were able to go down a lot, that would be good. And what this says is it puts a lower bound on it. That's what it does. There's no upper bound on this. You can perturb this by the slightest amount, and you can have P star equals plus infinity. And so there's no upper bound here. It's just that. Okay. So let's see what it means. And you have to be very careful because it's asymmetric. Oh, I should say this is a global result. This simply, you think about it as being interesting when u and v are small. Those are perturbations to the problem. But in fact, these can be gross perturbations. I can have u equals 7, ui equals 7. I can do all sorts of things, and these inequalities hold. So let's see what they mean. Well, first of all, it says the following. If lambda I star is large, then it says that if you tighten a constraint, let's forget the equality constraints, but let's tighten a constraint. That means if you tighten that, it means ui goes less than or equal to 0, and this is minus a negative number times a positive number. In fact, a large positive number and a pretty good. Well, here if I tighten it, it says, and then it says this thing will be worse. This will go up, right? This will be positive. This will go up, and in fact, it'll go up a lot. So, for example, if I tell you that lambda star is 100, let's say lambda 1 star, and I tighten the first constraint by a mere 0.1, then what it says is the optimal value of the new problem absolutely must go up by at least 10. That's the optimal cost, must go up by 10. And it can go up by much more. It can go up to infinity, for example, if by tightening that first constraint, that rendered the problem infeasible. Okay. On the other hand, if lambda I is small here, it says that P star does not decrease much if you loosen the constraint, right? So that says if this is a small number here, then it says if u, it says even if u is big and positive, it guarantees that the optimal cost can't go down much, right? By the way, the converse assertions you cannot say here. You can't conclude. Okay. And you'd make the same conclusions for these things for the inequalities, right? I won't go through them because actually the inequalities are probably more important to understand. Okay. Now, we can also get a local sensitivity result, and this is extremely useful in practice. Let's see what this does. So let's assume that the optimal value is differentiable at 0, 0. Now, by the way, there's many cases where it's not. So this is not just a mathematical pathology. This can occur in real problems, right? And let's see then it turns out that we can say what lambda I star and nu I star are exactly. They are the partial derivative of the optimal cost with respect to ui with a negative sign, and the same for nu I star, and that's it's partial p star, partial vi, and that's also with a minus sign. Okay. Now, how do you know that? Well, that's easy enough. We simply subtract these two things, divide by t, and this thing is this. I let t go to 0, being positive, right? This says this number here is actually always bigger than that number, and therefore its limit is. And here, if I let t go up, this number here is always less than minus lambda I star. Therefore, so is this limit, and therefore the limit is equal. These are just equal to minus lambda star. And the picture would look something like this. Here's a single constraint. F1 is less, F1 of x is less than or equal to u. That's the perturbed version. And this gives you P0 star, right? So that's P star of 0. That's the original optimal value. Now, you can see now that as you move, as you loosen the constraint or tighten it, if you loosen it, of course the objective goes down. By the way, that requires you to re-optimize, right? So everything here is with the idea that you change the constraints and you solve the problem again. Doesn't mean keep the same x. If you tighten the problem, the optimal value of p goes up. And it is smooth here and differentiable. And you can see here the optimal Lagrange multipliers may be, let's say, 3, right? Because it's the negative slope of that line, right? And what the global result here says, what this global result says, is it gives you the following inequality. It simply says that this curve P star of u is convex. That's what it says. And it says that, in fact, the one given by the Lagrange multipliers here is a tangent. That's essentially what it says. And you can see how it could be that, for example, here lambda star is about 3. I'm just guessing from the picture here. This P star could go up to plus infinity, just like that, right? And then what I could do is say, well, I'm going to tighten that constraint a little bit, right? And in fact, the value of P star there, it could be plus infinity. It means the problem is infeasible, right? And it's also true that this could go like that. And that means lambda star is 3. I would loosen it considerably, sort of expecting the optimal cost to go down, but it doesn't go down that much. Okay? So this is the idea. Now, now say something about the practical import of this. What we're going to see later is the following. When you solve a convex optimization problem, typically, at absolutely 0 cost, you will get a set of optimal Lagrange multipliers, optimal dual variables. It's automatically returned with most methods and things like that. And that's actually unbelievably useful in practice, because what happens is it means that you have a bunch of constraints. We can, by the way, check our complementary slackness condition with this right now. For example, if I have an optimal point and f1 of x star is -1, that means the first constraint wasn't active. And now imagine that I perturb the right-hand side. Instead of 0, I plug in -0.1 or +0.1. It won't make any difference. And that tells you partial p star partial u1 is 0. But that says exactly what complementary slackness says. It says that if the first constraint is slack, the first optimal dual variable absolutely must be 0. Okay, so that's quite highly consistent with this. Back to this practical use. So the practical use goes something like this. You have a big problem, you solve it, and it's a whole bunch of constraints. Let's suppose they're inequality constraints, and you look at them. Some are slack, some are tight. Okay. Well, the slack ones, we know what it means. What it means is that those inequalities, we impose them in the problem, but we didn't need to, in a sense, because they didn't affect the optimal value. Okay. By the way, that does not mean you wasted your time, because you didn't know ahead of time before you solved the problem that they were going to be slack. Okay. But now you look at all the ones that are slack, and you ask yourself something like, what would happen if I tightened or loosened each one? And the answer can range from the following. If I tighten it a small amount, the problem will simply become infeasible. That's the extreme case. On the other hand, I could loosen an inequality considerably, expecting the optimal value to go down, and it won't go down very much. It might not go down at all. That could happen. Okay, so those two things can happen. But for small perturbations, these things tell you how the optimal value changes, right? And it allows you to actually, it's a beautiful interpretation. It allows you to say the Lagrange multipliers tell you how tight a constraint is. So for example, if I could solve a problem with, let's say, I'm doing circuit design and I want to satisfy something and minimize some objective. And what I'm going to do is I have two constraints, a power limit and I have an area limit. And when I come back, both of them are tight. That's it. So at a 50 milliwatt budget, your design comes back using all 50 milliwatts. It's hardly surprising. You had a 1 millimeter squared area constraint. You come back using 1 square millimeter. Okay, again, hardly surprising. You were given these resources, you use them. And the question then is, what this answers for you automatically is questions like this. What if I were to increase or decrease the area or the power budget, right? So, and in fact, what might happen is that lambda 1 star is 0.01 and lambda 2 star, right? This is power and this is area. And lambda 2 star is 100. That's extreme, but let's suppose that came back, right? Let's see what it says. What it says is that this says, now remember that the power and area constraints are both tight. They're both tight. They're you know, you gave 50 milliwatts, you used 50 milliwatts. You gave a square millimeter is what you used. So they're both tight. But what this says is that in some sense, the power constraint is less tight. Because this says, it probably says that I could decrease the amount of power I allocate to it and we could get just about the same objective, right? It also, a negative result says this, if I increase, suppose I say, you know what, I want better performance, I'm going to double the amount of power you get from 50 to 100 milliwatts. Surely, if I give you twice the power, you can get a better design. And what this tells you is that you cannot. Now, this tells you that what's really killing you in this problem is area. And so this says, this tells you for sure, if I were to have the area I gave you, like I said, nope, I'm sorry, we can't do it, the economics doesn't work, you can't have a whole square millimeter, I'm going to give you half. This is going to guarantee you that the objective is absolutely guaranteed to do a lot worse. So that would be it. Now, you could also say, oh, because it's so tight, it says that if I give you more area, you should do better. That's actually only a local result. It's not global. So for example, you'd expect it, and it might happen, but again, we don't know. It's a local result. So, okay. So the recap of that is that these optimal Lagrange multipliers, which come for free when you solve a problem typically, actually give you a very nice and indeed quantitative measure of how tight the constraints are. With 0, lambda I star, you know, if lambda I star is 0, meaning somehow it's not tight, right? And lambda very big, meaning it's a very tight constraint, very constraining. What we're going to look at first is the idea of duality and reformulations, right? So here, let me draw a picture here to show you how this might work. Let's take a problem P, like this. That's a primal problem, and then let's form some equivalent problem like this. So this bidirectional arrow basically says that P prime is some problem equivalent to P. Now you've seen lots of equivalent problems. And for example, you could eliminate variables, you could add new variables, you could, if an objective is non-negative, you might square it or something like that. Minimizing the square is the same as minimizing the thing as long as it's non-negative. There's lots of things, there are lots of ways to produce an equivalent problem, right? Okay, now duality, through duality, we can make a dual. So there's the primal problem and here's a dual. And of course we can do that down here, right? So this is D prime, right? So that's our original problem. This is our reformulation, right? And this reformulation could be simple. I mean, it could be also very sophisticated, right? Okay, now when you see a picture like this, then if you have any training in math or just sort of minimal aesthetics, you have an overwhelming urge to do the following, to draw an arrow like this, right? When you do, this is just, you don't need to know this, but it's not bad to know. This is called a commutative diagram. It says that basically you can get, that you could say that this dual can be found, two ways. It's either the dual of the primal, or you could go this way. You could reformulate the primal, form the dual of the reformulation, and then somehow that's related to this one, something like that. Now, of course, in some sense, D and D prime are related because they're related this way, right? So this is kind of this is very general, very vague idea of what you'd like to happen. Okay, so now I'll tell you the bad news is that this is completely wrong. This doesn't happen. This is not accurate, and there's in general no such thing. Now it turns out that's actually very good news, and we're going to see why in a minute. So it turns out that if you take a problem, in fact, at first it sounds strange. If you take a problem, actually just form a very simple variation on the problem. It's equivalent, right? You add a variable, you make the epigraph version. I mean, just something that's totally obvious, right? Where you just do something simple. Then it turns out that these duals can be wildly different. We're going to see examples of that soon. They can be wildly different, and at first that's too bad, right? Because you wanted the idea of a dual to be intrinsic. It's not really. It depends very much on the description of the problem. But we'll see actually that it's a very good thing, right? Because it opens up the ability, given a problem here, of forming many, many different kinds of duals. And the method is very simple. You take the original problem, you then transform it, often, as we'll see, in a very trivial way, and then form a dual of that transformation, and you get something completely different than if you had done the dual here. This one, for example, we'll see cases where this one is actually useful and informative, where this one is completely trivial and completely uninformative. So this is the big picture idea that we're going to look at. Okay, so let's look at a case. This is an extreme case, but it proves this. It illustrates this point. So here, suppose you want to minimize f0 of ax plus b, right? Well, there are no constraints. So what's the Lagrangian? Well, the Lagrangian is the function. I mean, that's the Lagrangian because there are no constraints, so we don't even have to. We have no dual variables, right? That's the Lagrangian, and now you're asked to minimize the Lagrangian over the primal variables. That would give you the dual function. All right, so you minimize that, and you get the minimum here. That's called p star. Okay, so the dual function for this is simply p star. Now, good news is we have zero duality gap, right? Because if I ask you to maximize the constant p star over, well, no variables, because there are no dual variables, that's easy to do. The answer is p star. And then you say, oh, hey, look at that. That's fantastic. That's the primal optimal that's the primal objective. So now you can see, but you can see that it's completely useless, right? Okay. Now what we're going to do is this. We're going to simply take this problem and rewrite it this way. Okay? So the only thing we've done here is you introduce a new variable y and a bunch of equality. This second constraint, it just says y is ax plus b. ax plus b. I mean, the equivalence of this problem and this problem is completely transparent, right? It's just totally obvious. It's so simple. It's ridiculous. And then you say, well, and this is, if you like, that's p. This is p prime in the picture I drew before. And now you say, let's find p prime star, which would be, I guess we call it d prime, right? So let's find that. So let's take this thing and form the dual. Well, the dual turns out to be this. And I'm not going to go into the details, but by now you shouldn't be surprised that something like this would happen. You can write it explicitly. It's maximize b transpose nu minus the conjugate here of the objective of nu subject to a transpose nu equals 0. Okay? So this one here is in fact, first of all, it's not, the dual of this one is absolutely silly, right? It's simply the constant, which is the optimal value. This one is actually useful, informative. It is not hard to imagine applications of this, right, where you're solving some gigantic problem and you just want a stopping criterion or something like that. So the point is you look at your algorithm, and if at any point you can find something that's in the null space of A transpose nu,
you simply evaluate this number, and that's absolutely guaranteed to be a lower bound on the optimal value here, right? So this is in a case where dualization and trivial transformation, they definitely don't commute, right? In this case, they do not commute. You get, if you transform it and then form a dual, you get something that is actually useful, interesting, informative. If you don't transform, you get something that's completely silly. Okay. Now here, I mean, we can work out the dual function here. You simply form the Lagrangian, which is this thing, and then you minimize over x is what happens, right? And if you minimize over, sorry, x and y, because y is a new introduced variable. If you minimize over x, this thing is either minus infinity or it's 0. If it's minus infinity, if A transpose nu is non-zero, right? If A transpose nu is 0, then this term drops out, and then you'll recognize this as related to the conjugate function of f0, right? So again, that's just a calculation, and you can check on it and all that sort of stuff. Okay, so this is a good example where a transformation before you apply, before you compute determine a Lagrange dual makes a world of difference, right? So, by the way, what this means is that while people talk a lot of times and they say, here's a problem, and then informally you'd say, the dual is this. It turns out that's really not quite right. That's loose speech. And often, well, it can mean this. I mean, technically, when you say the dual is this, it means you follow the script perfectly. You form the Lagrangian. You minimize over the primal variables to get a dual function, and you maximize that subject to lambda bigger than or equal to 0. Those are the Lagrange multipliers associated with the inequality constraints, right? That, in some sense, that you just turn the crank on Lagrange duality. That's the dual. But people are informal, and they'll allow you to do a little bit of a transformation before you form the dual, and even sometimes a little bit of a transformation after you form the dual. And this is just an aesthetic thing. So very often you'll be in a situation where someone will say, here's the primal, and here's the dual. And what they really meant to say maybe was, here's the primal, and here's a dual, right? And so that. And by the way, you'll notice that sometimes when you hear people attach a name to a dual. So they'll say, here's a quadratic program, and here is the Frank Wolf dual, or here is the, whatever it is, such and such dual, right? So that's your hint that they're being a little bit loose with the idea of a dual. So, okay. All right. Let's look at a couple of others. Let's take a norm approximation problem. So you want to minimize the norm of ax minus b. And again, we'll introduce an equality constraint. So we'll write this as minimize the norm of y subject to y equals ax minus b, where y and x are now the variables. By the way, I mean, we're going to see this again when we actually solve these problems. If you were confronted with this problem, you might have an overwhelming urge immediately to get rid of y, right? Because it's silly. Y is ax minus b. Why not just plug that in the top? And I mean, this problem has fewer variables, all this kinds of stuff, right? So you might be tempted to do that. And in fact, your training, your pencil and paper 19th century kind of silly mathematics education you've had up until probably recently, possibly until now, but certainly most undergraduate courses are like that. You would, of course, do that because, in the pencil and paper world or the chalkboard world, that's simpler than that. It turns out, though, that's often not the case when you're actually either solving the problem, we're going to talk about that in the last third of the course, or, in fact, even here, when you're actually doing things like forming duals and things like that. You're actually better off sometimes looking at a problem that appears by 19th century aesthetic to be more complex. You may be better off. We'll see why that is later. Okay. So let's, this thing, I mean, minimizing a function subject to equality constraint is this just a completely uniform dual, and it comes up in terms of the, you can work it out completely generally in terms of the conjugate of the function. And we'll get to that, but the conjugate of a norm is in fact the indicator function of the dual norm ball. And some of these things, by the way, should start lodging in your mind. I mean, that you should start building maps of things, and if not the exact details, then at least just patterns. You should know these patterns so that when you see a max in one, you should expect in a dual to see something like a probability distribution or something that sums to one, right? So when you see a norm in one, you should expect to see a dual norm constraint in the other. When you see a norm squared in one, you should expect to see a dual norm squared in the other. So you don't have to, I mean, it's the same if you see an equality constraint in one with A, you should expect something involving A transpose in the dual. So these are just general patterns. You can always just calculate. In fact, you should probably do that just to be sure you got it right. But these are patterns you should start. I don't memorize them, but you should at least start picking up on these high-level patterns. By the way, if you do that, what's kind of cool is you'll start seeing them in every other course you take, right? They won't call it the conjugate. They won't call it the dual. It'll have another name, but you'll look at it and you'll say, I've seen that. I know what that is, right? That's the dual. And you'll see it in, in your statistics classes, certainly in economics and in lots of classes, right? So, okay. So here, let's just work out the dual. And so here what you would do is you would you minimize the objective here, plus this is you put an equality constraint, nu transpose times an equality constraint, and that's all of this thing here, right, written out. And now we are asked to minimize over x and y. X is easy, right? And we keep using this very simple idea that, this Lagrangian here is an affine function of x. And as silly as it sounds, it's useful to know how to minimize an affine function. It's very easy, actually. Here's the answer. It's minus infinity, right? Unless the linear part of the affine function vanishes, right? So no problem here. This says, unless this vector, sorry, I meant to do these, right? Unless A transpose nu is 0, the minimum over x of this thing is minus infinity. Right? So, all right. So, and then if assuming A transpose nu is 0, then that term just goes away, right? So that tells you that you get something like this. If A transpose nu is 0, then you have the norm of y plus nu transpose here times, and I guess you could write this as y plus b or something like that, whatever it is. And oh, sorry, this one can just come. That's just a constant, and it can come out here, and you end up with something like this. And whenever you see the infimum of a convex function plus a linear term, you can rewrite that as a conjugate, right? Or in this case, we can work it out directly. A norm here is homogeneous. It's if you multiply something by 3, the value is 3 times the value goes up by a factor of 3. It's homogeneous. So is this. And so what happens here is if here nu is big enough in the dual norm so that you can make this thing any number that's negative, then I can make it minus infinity by homogeneity, right? And so it tells you that this thing here, which is actually related to the conjugate of the norm, is simply the indicator function of the dual norm unit ball, right? So you end up with this here. And so the dual of the norm approximation problem is this, is you maximize here, B transpose nu subject to A transpose nu equals 0 and nu star less than or equal to 1, right? And so we're making various assertions here. What we're saying is something like this. For this problem, if you find any vector by any means, any vector nu in the null space of A transpose, whose dual norm is less than 1, then B transpose nu is a lower bound on the optimal value of that problem, period, right? That's assertion number 1. Assertion number 2 is there actually is a value of nu here for which it's actually equal to the lower bound, right? And in fact, by carefully analyzing what would happen here, you can actually recover partly you can recover what the optimal x is if I gave you the optimal nu. So this is the idea. Another variation on this is dealing with implicit constraints. So that works this way, is that you can, and there's a name for this sometimes. Some people call this a partial Lagrangian and partial dualization. So what that says is this. Here's my original problem, and it doesn't really matter what it is. It's a Yeah, it's a linear program. It says minimize C transpose X subject to AX equals B, linear equality constraints, and the constraint that X is in a box. So all the entries of X are between plus minus 1. Well, if I simply form the dual, I get something that looks like this. Okay? Fine. No problem. That's it. But there's another way to do this. What we'll do is we'll take these constraints. These are explicit constraints. And what we'll do is we'll put them implicitly in the objective. So I'll take this problem and I will transform it to this problem. And they are different problems. That's extremely important to understand. These are different problems, but they're equivalent. In this problem, there's only one equality constraint. And the objective is either C transpose X or plus infinity. But I've added in this thing here. And so it's very important to understand that, as objects say, you don't have equals equals here, right? This problem, if you ask how many constraints do you have, the answer is 2, right? If I say how many constraints do you have here, the answer is 1. If I ask here, if I say, problem.objective is linear, it's true here. And it's absolutely false here. Everybody see what I'm talking about? So, but they're clearly completely equivalent in the sense that, an optimal point here is an optimal point here and vice versa. Okay? So it's actually quite important to be very clear in your mind about equivalences versus being the same, right? So, okay, so these two, it's just really dumb. It's just a dumb way to, and the only way you would know any difference would be something like this. If I were to if I had this problem and I said problem.eval and I threw in an X which was outside the box, here it would return, what would be returned would be something like an error token, and it would say something like infeasible, right? And it would violate this constraint, right? Here, if I give you an X that satisfies AX equals B, but some X's are bigger than 1 or minus 1, right? Then what would happen in this case is I'd get a new thing. I'd get something back that said it would be an error just as well, but it wouldn't be the error. You're infeasible. In fact, what would come back would be a token telling me, oh, thank you, X is feasible. That's the good news. Bad news is it's out of the domain of the objective. Or another way to say it is the objective value is plus infinity. And if you're minimizing, that's about as bad as it can get. So everybody following this, right? So it's important to understand these are different. They're different, but also when you learn, when you're kind of in a situation where people are doing, street fighting type stuff, you don't even think about this, right? You just quietly do this or so. So if you take this problem and then you form the dual function here, you actually have you don't even have a dual variable associated with these inequalities, right? So you just get this. The dual function is this, but now this thing, if you like, I put it there, but it really should be an indicator function over here, right? It should be an indicator function of the box, right? Like that. So here it asks you to do this, but minimizing a linear function or an affine function over a box is trivial. We know how to solve that, and you actually get this, right? And so the dual problem after this minor reformulation is this. It says that the dual problem of this is that. It says maximize this thing, and everything works, right? Now, fact is, if you stare at this long enough, you will realize that this is the same as that. So, in this case, you do have that commutative diagram, right? The P, D, P prime, and D prime, you actually get a simple commutative diagram, right? But it doesn't always happen. Okay, so by the way, this thing here is called a partial Lagrangian. Or another way people would say what would happen is you say, I'm going to start with this problem, and I'm going to dualize, keeping the inequalities implicit. So that would be how people would say this. That'd be various descriptions for it. That's if people are being clear, right? Okay. Next topic is generalized inequalities. So far, everything in duality has happened with ordinary scalar inequalities. So constraint functions return numbers. If the number is negative, it's feasible. If it's positive, infeasible. But now we'll look at problems with generalized inequalities, right? So here, these are potentially vector valued. And the constraint is that that vector has to be negative or less than or equal to 0, but with respect to some cone. And the obvious non-trivial case is the positive semi-definite cone, right? So that could be a matrix inequality. Okay. And it turns out all the notation is set up perfectly. This is how you know you have good notation, is that everything looks exactly the same. You make a few minimal changes, and it's actually correct, right? So here, what you do is the left and right-hand side of that constraint is a vector. It's an RK, Ki. And so what we'll do is the associated Lagrange multiplier dual variable is a vector, okay? And the Lagrangian is the obvious thing. It's this. It's the completely obvious inequality that you'd have. By the way, if this was a vector equality, I mean, that'd be fine. You could put a transpose right here, and it would look exactly the same. So that's it. Again, it reduces in the case where they're scalar to just what we had before, but here it's a vector. Okay, so, and the dual function is absolutely identical, so it's great. So it means if you kind of wrote the, abstract enough software or whatever, your same thing that would work in the scalar case would just work absolutely transparently in this case, right? So that's good. Okay. Now the lower bound property, there's one subtlety. The lower bound property for general dual is this. If lambda is non-negative, then G gives you a lower bound on the primal problem. So these are vectors now, the lambdas, and it turns out that the correct way in which they're non-negative is in the dual cone. Now, first of all, you could have guessed that for many reasons. First of all, you should have guessed it on aesthetic grounds, and here are the aesthetic grounds. You're taking the inner product of two things. One is supposed to be negative in one inequality, in one cone. Then it actually sort of makes sense. And if you do sort of the very abstract mathematics and keep track of like row and column vectors and dual spaces and things like that, then you would be led, it would have to be that these things are in the dual cone. Of course, then you can just check because either these things are going to work out or they're not. So turns out that's the subtlety. Now, for the scalar case, the dual cone of R plus is R plus. So we don't see any difference, right? We just say if the inequality holds, then if you have a non-negative Lagrange multipliers, that's how that works. Okay. And to see how this works, the proof is essentially the same, except that you wouldn't have a transpose there. It's quite the same. It says that take any x that's feasible, and then let's form this Lagrangian like that. Well, these are 0, so this term just goes away. That's totally irrelevant. Okay, and now we look at, we'll look at this. So whatever this is, whatever this is for any x tilde, this is bigger than the dual function there, right? Because the dual function is the minimum of this over x tilde. So this is bigger than that. That's G. And over here, if you look at this, the key point is that you want to conclude that all of those numbers are less than or equal to 0, and that's correct because the fact that xi is feasible says that fi of x tilde is less than or equal to 0 in the ki cone. The inner product of that with a non-negative in the dual cone, that's what gives you that that's less than or equal to 0. So each of these are less than or equal to 0, right? So that's the key here. So it just works. Okay. So everything is the same, including, by the way, Slater's condition and things like that, generalized Slater. It's all the same. Okay. So the most important example of that is SDP, so semi-definite program. Semi-definite program, that looks like this. This is an inequality form. In inequality form, you minimize a linear function subject to what's called a linear matrix inequality. That says that a linear, a weighted sum of a bunch of symmetric matrices should be less than or equal to another matrix, right? And that's in the matrix sense, this inequality. So that's a semi-definite program. This is an LMI here. And so here we we're going to form the dual. So we have to have a Lagrange multiplier, something like a lambda. But it's a matrix because here, the left and right hand arguments are matrices, right? So it's going to be a matrix. We'll call it Z is a symmetric matrix. And the Lagrangian is this. It's C transpose X plus, and then it's going to be the inner product of Z and the part that is negative, which is this thing minus G. Now, the inner product of two symmetric matrices is the trace of the product, right? I mean, that's just that's the inner product of the two matrices considered as vectors in Rn squared, right? It's just the standard inner product. So I get this, like that. And now we do the same thing as usual. We minimize over x, right? But this is an affine function of x. So nothing could be easier, right? If you minimize an affine function of x, the answer is minus infinity, unless the linear part of that affine function vanishes, right? So let's look at the linear part. Or, I could do this with respect to each xi. Let's minimize over x1, this expression. Well, I get c1 x1 here, and I get trace z x1 f1, but I can take the x1 out. And so what I would get is c1 x1 plus, and then trace z f1, that's a number, times x1, and then plus a whole bunch of crap that doesn't depend on x1, right? That's what this Lagrangian looks like. Okay? I minimize over x1. That's completely trivial. The only option is that this plus this has to be 0, period. Okay? And that's true for any, the x1 is true for x2, it's true for x3. And so what I get is this. And all of these go away, and what I'm left with is minus trace zg. And so I get this. The dual function is minus trace gz, provided these equality constraints hold here. Otherwise, it's minus infinity. And I get the following dual, and it looks like that. It says that, and this is already a bit loose, but it says the dual of this SDP is this. And actually, it's kind of cool. This is an inequality form SDP, right? Because it's minimize a linear function subject to an LMI. And sure enough, you get an SDP over here, which is in equality form, right? So in other words, that the constraint is you have a variable that's non-negative and then equality constraints. And these are patterns that should start looking familiar to you. You've seen this in linear programming, right? If you have an inequality form linear program, the dual is a linear program with a variable that's non-negative with equality constraints. And vice versa, I might add. So these things should start looking the same to you. You should see patterns here. And by the way, people sometimes make little tables and cards and things like that you carry in your wallet that, says here's the primal and here's the dual. I mean, that's fine. But I think it's enough just to sort of recognize the patterns. And then, of course, in any given particular case, you better be prepared to work it out carefully and make sure it's actually true. So, okay. So that's it. So that's the dual. And this is not obvious. I mean, the assertion is not obvious here, that this is the dual of that. And if you expand that out into what you're really saying, it's not an obvious thing at all. These are things that maybe 25 years ago would have been things that basically the vast majority of people wouldn't know. So it'd be a shocking thing to study this problem 25 years ago. People would say, you shouldn't do that. That's hard to do. You can't do that. And then say, well, here's a dual. And you'd say, what do you mean by that? And you'd say, well, if anything feasible for here, that gives you a lower bound on that, and it's tight, and so on and so forth. It would have looked pretty complicated.